So torque, written as Greek letter tau. What do you have to do to count as a torque? What exactly is a torque in the first place? Like if I have some object and I say, I'm going to apply a torque to this, what am I presumably doing to it? Yeah, it's basically the rotational version of a force. Rotational equivalent of force. And because of that, the idea that it's the equivalent of force, but in a rotational motion instead of a translational motion, we can look at this in terms of what do we already know about force? Like in the translational situation, let's say you apply a force to an object. What does that do? If you apply a force to an object, what happens to the object? It accelerates, right? In other words, it causes, what exactly is acceleration? What's changing there?
Velocity.
Yeah, its velocity is changing. And on the other hand, if we take a look at torque, the rotational version, torque causes the rotational version of acceleration. And that really means I should specify force causes translational acceleration, which is a change to the translational velocity. Whereas torque causes rotational acceleration, which means it is changing the rotational velocity. And we should look into what those mean as well. Rotational velocity is basically a measure of how fast an object is spinning. For instance, if you've got an object that's spinning slowly, it's got a very low rotational velocity. If it's spinning faster, it's got a larger rotational velocity. And how do you think we would, rotational velocity or angular velocity. Rotational and angular are often used in the same way. Just like we might call this translational velocity or linear velocity. Translational and linear kind of mean the same thing. Rotational and angular kind of mean the same thing. So rotational velocity or angular velocity are both just terms meaning how fast the object is spinning. But let's investigate what exactly that means. If an object is spinning, how would you describe how fast it's spinning? Like what units would you use? If you wanted to describe how fast something is spinning, what units of measurement would you use for that? Yeah, it should be radians per second. Translational velocity would be meters per second. You're describing how fast or how far it moves each second. But rotational or angular velocity, you're describing how much it rotates each second, how much it spins each second. So that would be measured in radians per second. In other words, it's an angle divided by time. We usually write angular velocity as the Greek letter omega. And we define it as the change in angle, usually written as theta, divided by change in time. So how much the object rotates in radians or degrees, but we usually use radians, per amount of time. So for instance, if an object is spinning, let's say it makes one full revolution in 3 seconds. Let's say it makes one revolution in 3 seconds. We can calculate its angular velocity, its omega, as, what's one revolution in radians? Yeah, 2 pi. So 2 pi would be the change in angle if it makes one full revolution, divided by the amount of time it takes to do that, 3 seconds. In other words, 2 pi over 3, and formally the units are 1 over seconds because radians is unitless, but this would typically be read as radians per second. So 2 pi over 3 radians per second. But for purposes of the equations, radians is unitless. It would just be 1 over seconds. Alternatively, you could write the full revolution as 360 degrees divided by 3 seconds, which would reduce to 120 degrees per second. So you can measure this in degrees or in radians, or you could just say 1/3 of a revolution per second. Those would all be valid measurements of the rotational velocity. 1/3 of a revolution per second, or 2 pi over 3 radians per second, or 120 degrees per second. But usually radians work better for the equations. Typically, if you use degrees or revolutions, you have to use some sort of conversion factor. But if you use radians, it fits nicely into the equations exactly as is. Any questions on that so far? Also, would you expect the angular velocity to be a scalar or a vector? Does direction matter here? What do you think? If I'm describing how fast an object is rotating, do I need to specify a direction associated with that rotation? Yeah. If we have, like if I've got this object spinning at like 3 revolutions per second this way, and spinning at 3 revolutions per second this way are different rotations. Yeah, both clockwise and counterclockwise, and not only clockwise or counterclockwise, if I'm spinning it like this and I tilt it, it's now spinning around a different axis. That counts as a different direction of rotation. So we need to not only specify is it rotating clockwise or counterclockwise, but also what axis is it rotating around. So axis of rotation is really what we're going to be using here. For example, if this is rotating this way, this piece is moving this way, this piece is moving this way, this piece is moving this way. Each piece is moving in a different direction as it spins. So I can't really associate any one of those directions. Instead, we use the axis of rotation itself. For instance, this object right now is rotating around an axis in which direction? What axis is it rotating around? Yeah, we could say a y-axis. Or in 3 dimensions, we usually call the vertical axis the z-axis. The typical convention for 3 directions is x-axis, y-axis, and z-axis. So we'd say this is rotating around the z-axis, or we could just say the vertical axis. So what we're going to do, if we want to associate a direction with this, which we do, this is a vector quantity, and technically so is angle. The direction we're going to associate with this is either straight up or straight down, because this is rotating around a vertical axis. So what we're going to do to decide whether it's straight up or straight down, we're going to use this idea called the right-hand rule. As this spins, take your right hand and curl your fingers in the direction it's rotating. This is rotating like this. So I'm going to curl the fingers of my right hand in the direction it's rotating, and my thumb tells me the direction of the axis of rotation, specifically the direction of the angular velocity. So this rotation is an upwards angular velocity. No part of this is moving upwards. Upwards just represents the axis that it's rotating around. So that's the typical right-hand rule for rotations. If an object is rotating, curl your fingers in the direction it's spinning, and your thumb should tell you the direction of the angular velocity, which is just a description of the axis it's rotating around. On the other hand, if I spin it the other direction and curl my fingers this way, I get a downwards angular velocity. It's still rotating around the same vertical axis, but the 2 opposite directions of rotation correspond to up versus down. Or if I hold it like this and spin it this way, this rotation would be to, I guess that's my left, your right. or this rotation would be pointing this way. Or if I'm holding it like this, if I spin it this way, that would be in this direction. So that would be out of your screen. Or if I spin it this way, that would be into your screen. And again, that direction has nothing to do with the individual motion of individual pieces. It's the axis it's rotating around. So that's how we define direction for angular velocity. The direction is the axis it's rotating around, and specifically picked by the right-hand rule. Any questions on that directionality so far? And then we can also use angular velocity to define angular acceleration, or rotational acceleration, same thing. Angular acceleration, usually written as the Greek letter alpha, lowercase, also counts as a vector. And how do you think we would define angular acceleration? What would it mean if an object is angularly accelerating? What's it doing? Yeah, it's changing its angular velocity. Just like translational acceleration means the object is changing its translational velocity, an angular acceleration or rotational acceleration means the object is changing its angular velocity. The angular acceleration is the change in omega divided by the change in time. And since omega is a vector, the direction of spin matters. That means alpha is also a vector. The angular acceleration has a direction. And that means that your object is angularly accelerating if its angular velocity is changing. That might mean it's spinning faster. Like for instance, if I spin this slowly and then I make it get faster and faster and faster, that counts as angular acceleration. If I make it slow down, that also counts as angular acceleration. But also, even if it's spinning at a constant rate, if I tilt it, I'm changing it from this angular velocity to this angular velocity. So tilting it also counts as angular acceleration because I'm changing the direction of spin. So those all would count as angular acceleration. Angular acceleration means you're making it spin faster or slower, or changing the axis that it spins around by tilting it as it spins. Any questions on those terms so far? In order to make that angular acceleration happen, in order to make it spin faster and faster, or spin slower and slower, or to tilt the axis it's spinning around, to make that angular acceleration happen, what am I doing to the object? Yeah, applying a torque causes rotational acceleration. And that's exactly what I'm doing. To make this start spinning, I'm applying a torque. To make it spin faster, I apply more torque. To make it spin slower, I just apply a friction torque in the opposite direction. So torque is what's causing that change in angular acceleration. And note that, but to apply that torque, I was applying a force, but I was specifically applying a force where on the object? Where did I have to apply a force to this in order to make it spin, make it change its spin? Yeah, I've got to be somewhere away from the axis of rotation. If I just push on the axis of rotation itself, nothing happens. Or even if I push here, but I push towards the axis of rotation or pull away from the axis of rotation, it doesn't make any change to the rotation. I've got to apply a force that's far from the axis of rotation, and it's got to have some sideways component. That's what torque is. Torque is a force that is applied off of the center and has some sideways component. It's not just straight towards the center or straight away from the center. And it's also going to have to count as a vector in the same way that force counts as a vector because it's associated with acceleration, which has a direction. Likewise, angular acceleration has a direction, so torque has to be a vector as well. Torque has a direction associated with it. And let's take a look at exactly what that means, what you have to do to cause a torque. Like we saw with this, it has to be a force. It can't be just a force on the center. It has to be off center, and it has to be somewhat sideways. It can't be straight towards the center or straight away from the center. So torque is a force that is applied somewhere other than the center. Or we're usually going to call this the pivot point. If an object is rotating, the pivot point means the single point that everything's rotating around. So for instance, with this, the pivot point would be the exact center. Or if it was rotating like this, the pivot point would be this point right here, the point that it's rotating around. In general, the pivot point is going to be whatever single point is anchored in place as the rest of it rotates around that point. So for instance, for a door opening and closing, the hinge would be the pivot point. So the torque, in order to count as torque, the force has to be applied somewhere other than the pivot point. And it has to be at least somewhat sideways, at least partly sideways. Sideways in the sense of not straight towards the pivot point, not straight away from the pivot point. As long as these three things are true, then what you're doing is a torque. The force you're applying also counts as a torque. And of course, it still counts as a force. If you just got this object, I mean, I'm holding this here so that it doesn't move, but if I wasn't holding this, if this was just like floating in space and I tapped it, it would start to spin and also start to drift away. So that force that I applied counts as a force, causing translational acceleration, and a torque, causing rotational acceleration. So let's see if we can turn this into an equation. Let's ignore the vector, the directionality of this for now, though. Let's just take a look at the magnitude. You've got to apply a force. It can't be at the pivot point. So let's say we have just some object. Let's say just a, I don't know, a wooden beam or a metal bar or something. And it's rooted in place at one point. Let's say this location is the pivot point. In a sense that this is the point that everything's going to rotate around. If this rotates, it's going to rotate around that point. Maybe there's a hinge here, or maybe it's tied in place at this point. Maybe we just take this beam and put a nail in it, but it's able to rotate around the nail. In that case, all the distances are going to be measured from there. For example, if you apply a force to it, let's say you just grab it right here and pull straight up. Let's say this is a force acting on the object. We're going to measure the location of that force relative to the pivot point. Because first of all, of course, we want the force to not be at the pivot point. We want it to be applied somewhere else other than the pivot point. And the distance between the pivot point and the force is another vector that we're going to call r. That r is called the radius vector. And that's not exactly radius in the sense of radius of a circular object. It's radius in the sense of how far outwards from some central point. It's also called the moment arm, or sometimes the lever arm. So any of those terms, the radial vector, the moment arm, or the lever arm, just mean how far it is from the pivot point to the location where the force is being applied. And how would you expect the moment arm to influence torque? If you want to get the most torque, would you apply the force far from the pivot point or close to the pivot point? Yeah, you want to apply the force as far from the pivot point as possible. For instance, if you want to open a door, you don't push on the door at the location of the hinges. That's going to be really hard to open. You push on the door far from the hinges. This is why we tend to put doorknobs at that location, far from the hinges. So this involves radius as well. Larger force means you get more torque. Larger radius, the force applied further from the pivot point, also means you get more torque. Or to put it another way, the further you are from the pivot point, the more efficient your force is, the more torque you get per Newton of force. But also the direction matters here. In this case, this arrangement, this radius and this force is not going to get quite as much torque as it could. Which direction would you expect the force should be applied in order to get the most torque? Like if you were going to open a door, you wouldn't push on it on some diagonal. You'd want to push in which direction? If you could choose any direction you want for the force, which direction should we apply a force in order to get the most rotational effect?
Would it be tangential?
What do you mean by tangential in this case?
I guess like around the pivot point, like kind of like a tangent off of that rotation that it would make.
Yeah, because if you imagine this point, like as this object actually rotates, this point would trace out a circular path. You get the most torque if the force is along a tangent line to that circle. Because this point, at that instant, it's going to be moving in a tangential direction, tangent to the circle. So the force should be in the direction that that single point is about to move if you want to get the most effect, the most efficient result. So that's what we're going to do. If we want to get the most torque, you apply a force in a direction tangential to that hypothetical circle, which is also at what angle to the radius vector? What angle between radius and force would get the best result?
A 90-degree angle.
Right, 90 degrees, a perpendicular or right angle. So, and we're going to describe that angle as, let's say we call that theta. So theta is the angle between radius and force. Or alternatively, if you imagine extending the radius vector further out, you could also say this angle is theta. Those are different angles. You'd have like maybe 70 degrees versus 190 degrees. Or no, not 190, 70 versus 110. So they are different angles, but their relevant values will be the same. So you could actually use either one of these angles for theta and you'll still get the same result. Because the way we're going to work the angle into this, we want a function that's largest when we have 90 degrees offset. We want torque to be largest when theta is 90 degrees. And also, let's say you apply a force this way, straight outwards from the pivot point. If you just grab here and pull, how much torque are you applying? Like if this object is able to rotate, if I just grab and pull, how much torque am I exerting? Yeah, no torque at all. So if the force is parallel to the radius, if you're just pulling straight away from the pivot point or pushing straight towards the pivot point, you get no torque at all. And what angle would that correspond to? If you're just pulling straight outwards, what's the angle between radius and force? 180, I think I would call if it's in the exact opposite direction. So if you've got like radius this way and force this way, if you're pushing straight back towards the pivot point, then that would be 180. But that also counts as no torque. If the radius and force are in the same direction, like let's say you've got radius and force. In that case, radius and force are in the exact same direction. There is no offset, so we'd call that angle 0 degrees. So if they're in the exact same direction, that would be 0 degrees angle. If they're in the exact opposite direction, that would be 180 degrees. But either one of those leads to no torque at all. Because if you're pulling straight away from the pivot point, nothing rotational happens. If you're pushing straight towards the pivot point, you also get no rotational effect. And what trigonometric function would work there? What's a trigonometric function that returns the largest possible value when the input is 90 degrees and returns 0 when the input is 0 or 180 degrees? If we want the function to look like this. If we want 0 when the angle is 0 or 180, largest when it's at 90, that's going to be sine, right? We've got, because sine of 0 is 0, sine of 90 is 1, sine of 180 gets back to 0. And then beyond that, it gets into negatives. But we're not going to need angles larger than 180 degrees anyway, because as soon as the angle gets to 180 degrees, it's now on the other side, and you can just treat it as a smaller than 180 degree angle on the other side. But sine theta is going to work really well here. And for small angles, that is approximately the same as tangent of theta, but sine theta is going to be more accurate. So we can calculate the magnitude of torque, how strong the torque is regardless of direction, by multiplying the amount of force being applied times the radius, that is how far the force is from the pivot point, times the sine of the angle between the radius vector and the force vector. That should tell you the amount of torque every time, if you know the force and the radius and the angle between them. Any questions on that so far? And we can effectively use this as a definition. The magnitude of torque is radius times force times sine of the angle between them. And I'm just going to write this as the Greek letter tau without a vector sign. Without a vector sign, we just mean the magnitude, not caring about direction. It is a vector. We're just ignoring the direction for now and looking at the magnitude alone. So effectively the absolute value of the vector. And are there any circumstances where you would expect this to be 0? What would cause this formula to result in the answer being 0? Yeah, one of them is if the angle is 0 degrees or 180 degrees. So that would be if the force is pointing straight towards the pivot point or straight away from the pivot point. So you get no torque if the force is, if the angle is 0 degrees or 180 degrees. So if the force is straight away from the pivot point or straight towards the pivot point. More generally, if the force is parallel to the radius vector, either straight in the same direction or straight in the opposite direction. If the force is parallel to that moment arm. Or we could just say that symbolically by saying force vector is parallel to the radius vector. That would lead to no torque at all. And yeah, no distance. If that force could be applied anywhere, but if the force is applied at the pivot point, then distance is 0. If distance is 0, then torque is 0. If the force is applied at the pivot point, so if the force is applied at the pivot point, or if it's applied straight towards or straight away from the pivot point, that leads to no torque. Or alternatively, of course, if force is 0, you would get no torque. So of course, if there's no force, then you get no torque, because every torque is caused by some force. So if there's no force, you get no torque. If there is a force, but it's applied at the pivot point, then R is 0, so you get no torque. And if there is a force and it's applied somewhere else, but it's applied in a direction parallel to the pivot point, like straight away or straight towards the hinge, that would also lead to no torque at all. So all three of these have to be false in order to have a torque. You have to have a force. That force has to be applied somewhere other than the pivot point, and it has to be in a direction that's not straight towards or straight away from the pivot point. That's what I meant by having at least somewhat of a sideways direction. In other words, more formally, the tangential direction. Any questions on that so far? So this is one formula for calculating how much torque there is. It should always work, as long as you know the moment arm, distance, the force, and the angle between them. But that's not always practical. You don't always know that angle. It's not always easy to measure the angle. So there are a couple other ways you can look at this more geometrically. And this has to do with the idea of splitting the vectors into components. Let's say we have this same object. It still has a pivot point here. And let's say we're still applying a force at this location. But let me make that not exactly straight up and down. Let's say it's in this direction. And then, of course, we can draw the radius vector from the pivot to the location where the force is being applied. And I'm going to make two copies of this because we're going to look at this in a couple of different ways. So let me see if I can draw this out identically. And keep in mind that the radius vector is always drawn from the pivot point to the location the force is applied. Regardless of the shape of the object, all we really care about is where's the pivot point that it's rotating around and where is the force applied. So if we want to write these in terms of r times f times sine theta, r is typically pretty easy to measure if you can actually put up a ruler from the pivot point to the location of the force. The amount of force is usually pretty straightforward if you have like a spring scale or something to measure it. The angle can be kind of difficult to measure though. In theory, you could just put up a protractor and measure it, but it's not always easy to see the exact direction of the force. So sometimes it makes more sense to split these up into components. But we don't really want to split it up into the usual x and y components here. Because if you tried that, if you tried splitting this up into the usual x and y components, those x and y components don't really tell you much about the angle between the vectors. It's great for figuring out the angle this vector makes with the x-axis, the angle this vector makes with the x-axis, but what we care about is the angle between the vectors. And one way to look at that is if you imagine extending the radius vector, I'm going to ignore the rest of the beam itself here. If you just extend the radius vector, the angle we're talking about is the angle that the force makes with the radius vector or the extended radius vector. So that's theta. And the idea that we're measuring this angle suggests that we could be constructing not x and y components in the horizontal and vertical sense, but instead a component in the direction of the radius vector itself and a component perpendicular to that. So we're still splitting the force vector into components. We're still creating a right triangle with the force as the hypotenuse, the vector as the hypotenuse. But instead of the usual x and y components, we're using a parallel component that is parallel to the radius and a component perpendicular to the radius. And these are sometimes called f parallel and F perpendicular, or sometimes just abbreviated to F perp. So you've got the parallel component, F sub, and then a parallel sign, and the perpendicular component, F, and then a perpendicular sign. Or in text, they usually written as F sub parallel and F sub perp. Parallel, perpendicular. These are also sometimes written as the tangential component. F tan, that's the tangential component in the sense that, again, if you were to draw out a circle with this as the radius, the perpendicular component is in a direction tangent to that circle. And then the parallel component is also sometimes called the radial component, F radial. Radial in the sense that it's in the same direction as the radius. So we're splitting the force up into components, but not the usual X and Y. Instead, the parallel or radial component and the perpendicular or tangential component. We're essentially setting up a new coordinate system using the radius as one of the axes. And the reason we do that, if we do a little bit of trigonometry here, we have a sine theta in this formula. What would sine of this angle represent in this triangle? What ratio of sides would sine of this angle look like? Which side over which side? Yeah, it's opposite over hypotenuse because it's sine. So that's the tangential component, F tangential or F perpendicular, divided by F itself. Which means if we solve for F perpendicular, we just get F times sine theta. So the perpendicular component is the force itself times the sine of the angle between them. And the reason why I was saying it doesn't really matter if you use this angle or this angle is that both of those angles will have the same sine. Sine of, like if you take, let's say this is 30 degrees and this would be 150 degrees. Sine of 30 degrees and sine of 150 degrees end up being the same thing. So it doesn't really matter which of those angles you use. I would usually use the acute version, the one less than 90 degrees, just because that's easier to visualize, but either way works. Also, F sine theta is most of the torque formula anyway. What's the only thing that's missing? Yeah, and we could just multiply that in. We could multiply both sides by R. So now we have R times F perpendicular equals R times F sine theta, because F sine theta is just the perpendicular component, but RF sine theta is the torque. So this provides another way to calculate the amount of torque. One way to calculate the torque is, instead of RF sine theta, you take R exactly as is, and then take just the perpendicular component of the force. So in this case, you would essentially ignore the force itself, and of course ignore the parallel component. The perpendicular component is what actually matters there. So one way of calculating torque is the entire radius exactly as it is times just the perpendicular component of the force. Because the perpendicular component is what makes it rotate anyway. The parallel component doesn't really influence torque at all. So that's another way to calculate torque. Radius times just the perpendicular component of the force. Any questions on that so far? And then another way to do this that's sometimes useful, instead of keeping the radius and splitting up the force based on the radius, we could instead keep the force exactly as it is, but split up the radius vector into components based on the force. So you could treat the force vector as the foundation of a new coordinate system, a new axis. And we could split up the radius vector into a component perpendicular to the force, so we draw at a right angle, and a component parallel to the force. So again, we're creating a right triangle, but now using the radius as the hypotenuse and creating one side that's parallel to the force, which we'll call R parallel, and a component perpendicular to the force, which we'll call R perpendicular. So we're keeping the force exactly as is, but we're splitting up the radius into a parallel component and a perpendicular component. And it might help to imagine extending the radius outwards as well, because that way, this is the angle we were calling theta. But since these are vertical angles, this angle will also be theta. And now in this new triangle, what would sine theta look like? Because we still want to use sine theta in this formula. Sine of this angle would be what side over what side? Yeah, the tangential component, R perpendicular, divided by the actual magnitude of the radius, R. And again, we can multiply both sides by R and get R sine theta equals the perpendicular component. And once again, this is almost the formula for torque. All that's missing is an extra times force. So if we multiply both sides by force, F times R times sine theta is torque. And we get F times R perpendicular. In other words, an alternate way to calculate torque, instead of multiplying R times F times sine theta, we could take the entire radius times just the perpendicular component of the force. Or, as we've just done here, you could take the entire force times just the perpendicular component of the radius. Ignore the radius, ignore the parallel component, just look at the perpendicular component of the radius times the force itself. Any questions on that formula so far? And keep in mind, these are all effectively the exact same formula. They're just three different ways of writing it, but they're all geometrically equivalent, just different ways of splitting up the vectors. And these can be useful in different situations. There are many situations where it's inconvenient to measure the distance, but it's very convenient to measure the distance perpendicular to the force. One very common example of this is the force, if the force happens to be gravity. Gravity is going to be straight down, so the perpendicular component of the radius is purely horizontal. So if you have, let's say, a bridge or something with a car putting weight on it, the car's weight is pushing straight down. So instead of measuring the diagonal radius, you would just measure the horizontal out to the spot directly under the car, or whatever is putting weight on it. So this F times just the perpendicular component of R is often much more useful in actual practical applied situations. But they still all give you the same result. It's really just a matter of what information do you have. Any other questions on that? One last thing really quick. We've been looking at just the magnitude of torque, but it's a vector. So what else does it have other than just magnitude? Vector should have magnitude and direction, yeah. So we're going to need to have a direction to associate with the torque. And for the direction of torque, we use another right-hand rule. Let me tidy this up a little bit. If we have this radius and this force, what you want to do for this is you want to choose a direction that's perpendicular to the radius and perpendicular to the force. If the radius is this way and the force is this way, the only possible directions perpendicular to both of these would be either straight out of your screen or straight into your screen. So those are your options for torque in this case. To choose one of those, we're going to use another right-hand rule. The typical way to do this is take your right hand, put it at the pivot point, stretch out your fingers straight along the direction of the radius, and note that right now I can still pivot my hand around, but I want to be able to curl my fingers in the direction of the force. Once again, put your hand at the pivot point, stretch out your fingers straight in the direction of the radius, and swivel it around until you can curl your fingers in the direction of the force, and then your thumb will tell you the direction of the torque. So in this case, radius, force, torque would be straight out of the board. So we'd say the torque is out of the board in this case, and that's typically written as a circle with a dot in it. Circle with a dot is representing a vector or an arrow pointing straight out of the board. That's supposed to represent what it would look like if you were looking at an arrowhead that's pointing straight towards you. Any questions on that so far?
So the opposite direction would have like an X?
Yeah, an arrow pointing straight away from you is typically drawn as an X in a circle, or sometimes just an X without a circle. But that's supposed to be like you're looking at the back end of the arrow. So this is the fletching, the arrow, the feathers on the other end of the arrow and the back of the arrowhead. Once again, right hand rule, let me draw out a different arrangement that might be more practical. Let's say you've got a radius this way and a force pointing, let's say, this way. So presumably the pivot point would be here. In order to do the right hand rule with this, first of all, before you even do the right hand rule, radius and force being in this arrangement suggests that the torque has to be either straight out or straight in, because the important thing is the torque is going to be perpendicular to both radius and force. But to choose one of those, the whole point of a right hand rule is just choosing one of those two. Put your hand at the pivot point, stretch out your fingers straight along the radius vector, so straight towards where the force is being applied, and swivel your hand until you can curl your fingers in the direction of the force. Radius, curl in the direction of force, and your thumb tells you the direction of the torque. Any other questions on that? All right, then I will see you next week.